wanted to work through an example that involves reflection of a curved mirror. When we do rays tracing or reflection of a curved mirror, we draw four distinct types of rays. So there's a pair of rays that involve either going in parallel to the optical axis or heading out parallel to the optical axis. In one of them, you head in to the mirror parallel to the optical axis, and you head out either through the focal point or as if you're coming through the focal point of the lens. The other one is that you head into the mirror either through the focal point or towards the focal point of the mirror, and then you head out parallel to the optical axis. So that's a pair of rays that you can draw. That's the brother and sister pair or the cousins pair that involve parallel in, parallel out, or through the focal length, focal point in, or through the focal point out. The other rays that you can draw are the simplest one, I think, is one that involves the radius of curvature. You head in through the radius of curvature, you head out through the radius of curvature. Or sometimes you head in towards the radius of curvature and you head out as if you're coming from the radius of curvature. But it all involves the radius of curvature. And in that case, the ray in and the ray out are along the same line or along the same path. They're just in opposite directions. And then a fourth ray that you can draw, this is the ray that strikes the mirror at the optical axis, at the center of the mirror. It reflects off the mirror from the optical axis at the center of the mirror. And you draw it such that the angle of incidence of the ray equals the angle of reflection of the ray, i.e. obeying the law of refraction. Okay, well, that was a bit of summary on what the various rays are that you can draw when you're ray tracing with mirrors. Let's try and answer some of these questions. So in question number 1, it says, for the 3 ray diagrams drawn below that all involved a curved mirror and an object, we've got to sketch ray number 3 in this list of rays here. Ray number 3 in this list of rays here, that's the ray that goes in through the radius of curvature, would come out through the radius of curvature, or sometimes it goes in towards the radius of curvature and comes out of the mirror as if it was coming from the radius of curvature. So let's try this for this picture upstairs on the left, this picture upstairs on the right, and this picture downstairs here. So here's the object over on the far left in this picture. And here's the lens, is the mirror. This is a concave mirror. The shiny surface is on the left-hand side here. And we're going to draw a ray that heads in towards the mirror through the radius of curvature, strikes the mirror, and it will head out through the radius of curvature in the opposite direction. So for this ray struck the mirror at 90 degrees to the mirror's surface. This ray makes a 0-degree incident angle with the mirror's surface. It makes a 0-degree reflected angle with the mirror's surface. And so the incident and the outgoing rays are along the same line here. Second case, here's the object. Here's the curved mirror. Again, it's a concave mirror. The reflective side is on the left-hand side here. And so let's try and draw this ray. Now, we can't go towards the mirror through the radius of curvature. What we have to do is go towards the mirror as if we are coming from the radius of curvature. So that would be a line that goes something like this. And then it's going to reflect back along that line. So this is the outgoing ray. And so that's how to construct that ray when you're inside the radius of curvature. You draw the ray as if that ray is coming from the radius of curvature. Again, this ray strikes the mirror 90 degrees to the mirror's surface. It's making an incident angle that's 0 degrees, a reflected angle that's 0 degrees. It obeys the law of reflection in that the incident and reflected angles are the same, and it's a ray that heads in the same direction that it heads out of, just 180 degrees apart from one another. Third diagram down here. Okay, now here on the right is the object. It must be that this case, the right-hand side is the reflective surface of the mirror. And this, unlike the first two cases, this is a convex mirror rather than a concave mirror. So the concave mirror, the radius of curvature, the focal point are in front of the mirror. In both cases, the radius of curvature and the focal point are in front of these concave mirrors upstairs. This one, the radius of curvature is now behind the mirror, and the focal point would be behind the mirror. So let's draw a ray heading in now. It's going to head in towards the mirror as if it's heading towards the radius of curvature. So something like this. Strikes the mirror, can't go behind the mirror. It's going to head outwards from the mirror as if it was now coming from the radius of curvature. So something like this. And so that's that special ray, number 3 in our list of rays. Okay, this part of the worksheet, we've got to draw the ray that heads in parallel to the optical axis and then reflects off the mirror either through the focal point or as if it's coming from the focal point. And we're going to do this for this situation depicted over here on the left-hand side, and then we'll do it for the situation depicted over here that's on the right-hand side. So downstairs here, that's the object. Over here on the right, that's the mirror. The left-hand side of this mirror is the reflective surface. The right-hand side is behind the mirror. And here's the radius of curvature. The focal length of a mirror, or the focal point of the mirror, is at a position that's half the distance from the mirror to the radius of curvature. So the focal point, I'm going to mark that, is about here. And then the ray that we're asked to draw is the ray that travels parallel to the optical axis. So this ray here, traveling from the left to the right, traveling parallel to the optical axis. And then it's going to be reflected off the mirror to pass through the focal point. That's the rule for drawing that ray. And here's that ray. And if we look at that ray, let me add one more line here. And add a line that is approximately the normal to the mirror where the ray struck the mirror. What we see is that this way of constructing this ray, parallel in through the focal point out, naturally leads us to a ray where the incident angle, measured with respect to the normal, it's this little angle upstairs here, equals the reflected angle measured with respect to the normal. So we see here that theta I upstairs, theta R downstairs, the incident reflected angles are equal. That's the law of reflection. Second situation. Let's go over here to the right-hand side. And in this particular case, here's our object on the far right. Here's our mirror. This is now a convex mirror. The right-hand side is the reflecting place, the shiny face of the mirror. And then the left-hand side is behind the mirror. And it's a convex mirror. So a convex mirror has a radius of curvature behind the mirror, would have a negative value, and its focal point or focal length is half the distance to the radius of curvature. That's also behind the mirror. That's located about here. So now let's draw the corresponding ray for this arrangement. We've got a ray coming in parallel to the optical axis, so something like this. It strikes the mirror. Well, it can't reflect off and go through the focal point because that's behind the mirror. Rather, it reflects off and appears to come from the focal point. So a ray something like this. This ray here, extrapolates back to the focal point. And so that's how you construct this ray for a concave mirror. Again, let me add one more line to this already ugly picture. Is this line here. This is the normal to the mirror. It's 90 degrees to the surface of the mirror. I've drawn it at the location of the reflection. And it's with respect to this line that we measure the incident angle, theta I. We measure the reflected angle, theta R. And again, this rule for drawing this ray arranges that we have the law of reflection, that the incident angle and the reflected angle, to the extent that I can draw them accurately, are the same angles. On this part of the question on the worksheet, we're asked to draw all of those four rays, the cousins or the brother and sister in parallel or out parallel, in through the focal point or out through the focal point, and then that ray that travels through the radius of curvature, or as if it comes from the radius of curvature, where the direction out is along the direction in, just in the opposite direction. And then finally, that ray that strikes the center of the mirror, it strikes the location of the optical axis passing through the mirror, where you can sketch most easily the fact that the incident angle and the reflected angle are the same. Let's draw all those four rays. I'm going to first, though, just mark the radius of curvature and the focal point of our mirror, which is behind the focal length and behind the mirror. And then I'm going to start sketching these rays using these 2 points that I've indicated here. So one ray we can draw is this one that heads in parallel to the optical axis, is this ray here. And then it will head out as if it was coming from the focal point. So something like this here. This appears to come from the focal point. This ray has a friend or a partner or a cousin. It's the ray that heads in towards the focal point. So something like this ray here. And then heads out parallel to the optical axis, this ray here. So those are the two rays that are cousins. We've drawn those. And then we've got a ray that heads towards the radius of curvature. So this is a ray that's going to head in something like this towards the radius of curvature. This ray reflects straight back off the mirror in the direction it came from. And so here's the outgoing reflected ray here. It's heading off in this direction. And there's finally one more ray that we can draw. It's the ray that heads towards the center of the mirror, the optical axis. So it's this ray here. And it's going to be reflected at an angle where this reflected angle downstairs here is equal to this incident angle upstairs here. And so these are my four rays that I've drawn. Maybe I'll label them. So the ray that went in parallel to the optical axis, that was ray number 1. The ray that came out parallel in the notation on this worksheet is ray number 2. The ray that heads towards the radius of curvature and heads out back away from the radius of curvature, that's ray number 3. And then finally, this was ray number 4. So over here on the far right is my eye and my brain. And my eye and my brain are constructing where these rays appear to come from. Let's see where they appear to come from by tracing some of these rays backwards. Here's the horizontal ray that I'm tracing backwards. That's pretty easy to trace that backwards. Here's this upgoing ray. Let's trace that backwards. Here's the cross here. That's an indication of where the image is located. Let's check it with some of the other rays. Let's take this downward going ray here. Also appears to come from that location. And finally, one more check. This ray that we constructed going to the radius of curvature, let's trace that back. And that also appears to come from that location. And so this point here, to the extent that I can draw it accurately, which is a limited extent, I admit that, tells us that the image of the object is located over at this location here. So here's the image. This is the image distance from the mirror. We normally call that Q, sorry. And here's the object. It was the original object. We call that object distance P. Finally, we're going to do a calculation of that same construction of the location of the image for that particular object in that particular mirror. But this time we're going to work with the mirror equations and the magnification equation rather than the ray tracing. So if I read this question, it tells me that an object is a distance r away from the mirror. So P equals r. And that that distance r is the radius of curvature. So this location here, C, that's at a distance r. So that means that the focal length of this mirror is also related to r. It's half r. Now I've got to be careful here. Because we're behind the mirror, this focal length is negative. And also, because I'm behind the mirror, although I'm not going to use it in this calculation, this radius of curvature, that's also negative. So I should indicate that this is negative r. So with this information, I'm going to solve for the position of the image of this object. Obviously, it's going to be in terms of r because that's just a symbol, not a number. And I'm also going to solve for the magnification of the object. It turns out that that is just going to be a number. It's just going to be a size. Okay, so let me write down what we concluded from the sketch. The focal length is minus r over 2. It's negative because it's a convex mirror. The object position is r, and we want to find the image position. So let's write down the mirror equation. The sum of the inverse of the object position and the image position equals the focal length. Let's turn that around. We want to find Q. So let's first find 1 over Q. 1 over Q is going to be 1 over F minus 1 over P. Just rearranging the equation. If I fill in that P is R and F is minus R over 2, let's do that. We're going to get minus 2 over R. So that's the focal length term. Minus another R. And that's going to tell us that, that 1 over Q is actually minus 3 over R. And so that actually tells us finally that Q, if I invert minus 3 divided by R, is minus R over 3. So it's going to tell us the location of the image in terms of the location of the object. It's a third of the distance from the mirror. So it's going to be somewhere around here. And I put it behind the mirror because it's a negative number. So a image object position behind the mirror is a negative number. What about the magnification? Magnification equation is that the magnification is minus the ratio of the image position divided by the object position with this minus sign here. So it's the negative of the image position divided by the object position. Q is minus R over 3. P is R. When I fill in the minus R over 3 in the numerator, the R in the denominator, the R's are going to cancel out. And the minus sign in the equation is going to cancel with the minus sign for Q. And I'm just going to get 1/3. And so we find the magnification is 1/3. If I want to add this result to my sketch, and if we can remember how I drew it before, I'm a third of a distance from it behind the mirror, but the object is in front of the mirror. So that's somewhere over here, I would say. And I'm 1/3 of the size. And so this looks like the image that we found with the ray tracing in the previous part of this problem. Anyway, I'm going to end there. We talked about images formed by curved mirrors. We talked about how to sketch the images formed by curved mirrors with ray tracing. We talked about the characteristic rays we normally sketch. We talked about the mirror equation, the magnification equation that we can use to numerically calculate the properties of an image.